My name is Anna Steffi, and I am part of Group 19.
I'm Zach Barnett, and I'm a part of Group 19.
I'm Alana Judd Wallace, also Group 19.
I'm Zoling Jia in Group 19.
And this is for recitation 9 in physics. And we have the shared documents. And so we're given the problem of a spring with a stiffness and a relaxed length that stands vertically on a table. We hold the mass, very slowly lowering the mass onto the spring until the spring is compressed to the point where it supports the mass at rest by itself. You can let go. How much is the spring compressed at that point, and how much work did you do lowering it? So how did people approach this problem? Like my work.
It seems like we all approached it in a pretty similar fashion. Like we, for finding the value of S, we all took the equilibrium point and realized that the net force at that point is 0, and we were able to set the spring force equal to the force of gravity, so on and so forth, solve for S. And then looks like we all kind of use the energy principle to solve for work using kinetic energy, gravity, and spring potential energy.
Mm-hmm.
Yeah, and then the changing kinetic energy of the system is 0, so that simplifies things.
Mm-hmm. Yeah, because at both points that we're evaluating between, it's at rest. Yeah, just to identify the system. And Mike, in this case, whenever I was solving this, I put as the spring, the block, and the earth. And yeah, I think that I see that in everybody else's work too.
Yeah.
So yeah, that looks great. And then in the part 2, it's like we're holding the mass. This time you let go of the mass. What is the magnitude of the spring's compression when the mass is at its lowest point? I approach this really similarly with no work and the system being at rest to get rid of kinetic energy when I use the energy principle. Did other people use this the same stuff?
Yeah.
Yeah, I see everybody's answers.
Yeah, mine looks different. I just did it weird, but the negative isn't supposed to be there. I did mess that up, but the actual answer itself is the same.
Okay, I'll make note of that. Yeah, everybody's work looks beautiful. So, and then I think the last part, this time, start with the mass sitting in equilibrium on the spring and push the mass down very slowly until it's at rest. The mass is not attached at the end of the spring, so it shoots off high whenever you let go. And we're tasked with finding speed. And so I think how I started off this problem is, in the past, we've always been talking about how the final and initial states of kinetic energy are at rest. So that's what we can use that to our advantage. But here, even though work is the same, whenever I need to find speed, I know that I need the 1/2 mv squared. So I knew that that was going to be a factor. So that's just how I started off this problem.
Yeah.
Mm-hmm.
Yeah, because between stages 2 and 3, where the spring is compressed and where it launches off, we know that kinetic energy changes at that point, where it normally doesn't in the previous problems. So you're right there, and we use kinetic energy, but we know work is also 0, so we could solve pretty easily for V there.
I see everybody found the force, the distance that the force is acting through. Decent, or just, yeah, that's my work.
And then, well, how did everyone get work in that? Because that was the 2-step problem. It was solving for velocity and solving for work as well.
Let's see. Interesting. I got something a little different. I actually did get something different. I got what Alana got. I recognize this as Alana's work. Mine looks like that. I wonder if yours just looks different though.
You mean my velocity or my work?
Your work.
What did you get?
Oh,
for
no,
the-
no, 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 no. Let me look. No, never mind. Everything looks the same.
Okay, good.
Yeah, everything looks fine. Okay, never mind. And then problem 2, this time you're holding the mass at rest with the spring compressed from its natural length, twice as far as what you found in part 2. The mass is not connected to the spring, so once again, it like shoots up, and then we have to find this new length that it reaches before falling back down. How did, I don't know, you approach this one, guys?
I was a little confused, so I don't know.
Yeah, this one is a weirder one, but it's a similar principle, I believe. You kind of use the energy principle like we did before, and we replaced delta y with our own equation that we came up with based on
Mhm.
what we were trying to solve for, which is the change in L. And I have it kind of in the top right there. Delta y equals the whole equation written out there. And then plug that into the equation and then solved for L minus L naught. And that was the equation I got at the end there. The length of, or the distance between the spring compressed and the mass at its highest point.
Interesting. So I think I put so I had the equation. First of all, I got a different answer.
Mhm.
And I got the same answer as Gia, it looks like. Although his work is like a lot cleaner than mine, which is nice. But like, once again, our final initial states are 0, still using the energy principle. And for this S2 lowest is just our value that we had previously found, simplified. And then I'm solving for the delta y, which should be the height. But this is not the total height. Half of this would be the height, which I put down as for mg over the spring constant, which is what he has as well, which is really nice. But yeah, let me see. Yeah, so I think the only difference is right here, I had just delta y, and you put in L minus L naught plus 2.
Yeah, I did because my understanding was that we were trying to solve for L minus L naught because that's the distance the mass was off of the spring at the end. And I think that's what we're trying to solve for. So
Okay. So does anyone have any problems with this or anything that you wanted to bring up real quick? Or okay. So I think that was it. Does everybody like what we put in the document? I've made like 2 notes about like the negative sign that we'd seen
sure.
and stuff, but otherwise it looks good to me.
Okay. Yeah.
Yeah,
All right.
I think very good.
All right.